so far we have looked at different types of data encoding techniques. In other words, how do we represent the basic forms of data that a computer would work on, right? We started off by saying that probably the single most important or relevant type of data for a computer is numbers. So we start with integers, look at different ways of representing them, the trade-offs that are involved, and then we looked at how can we represent real numbers and also in terms of characters, right? So in other words, just text. If I want to represent text that is human readable and human understandable, but I want to represent it in a way that a computer can process, what are the ways of doing it? And ultimately the main thing to keep in mind over there is what we are finally doing is some kind of an encoding, right? So we take whatever it is that we want and reduce it to a form of a number, right? Integers of course naturally are numbers, but everything else what we are doing is we are converting it effectively into an equivalent number and then saying, okay, this number in the right context should be interpreted in this form. Now, so far we looked at data, and the natural extension is, what else does a computer use? It uses instructions, right? We give it instructions on how to go about processing data. The natural question that comes therefore is, can those instructions also be encoded in a similar manner to how the data is being processed? So let's recap quickly, what do we mean by instructions? These are the basic operations defined for a CPU. CPU, a central processing unit, a processor, a computer core, many different terms for the same thing, but at the end of the day, that's what we mean is the part of the computer that actually processes instructions. And it's sort of a circular definition if you look at it that way, but it is the part that can interpret what we want it to do and actually execute those instructions. Okay. So what are the types of instructions that we have seen so far? Arithmetic and logic instructions, addition, subtraction, comparisons, shifting numbers and so on, right? Loads and stores, and the reason for this of course was because we found that the local storage available inside a processor is limited, and if we want to have access to much larger stores of memory, we need to go outside, and therefore we need to effectively treat that as a separate unit, an external memory, from which we load data into our local storage, process it and write the data back as necessary. So those are the load and store or the memory kind of instructions. And finally, we also have control flow, which are branching instructions, right? We have executed a set of instructions up to a certain point, and now we find that we need to jump somewhere else. We need to either repeat a set of instructions once more, or based on a certain condition, we need to change the flow of operation. So control flow is the next big class of instructions that we can think of for a processor. So this is once again a recap of the program that we developed to solve the problem of adding n numbers, right? And the assumption was that we have all of these numbers that are stored in memory somewhere, and what we want to do is to add all of them and finally get the result into another location in memory. Okay, of course whether we finally put it back into memory or not is secondary, but that was how we wrote the program. And if you recall, the way that we constructed this was we basically set up some temporary storage space for a counter which would keep track of whether we had finished adding all the values, another temporary storage which would actually keep the sum that we are interested in computing, and then we start loading in the values from memory, adding them into the register that we have constructed so far, incrementing the counter to keep track of how many values we have added, check that counter to see if we have finished the work that we started out wanting to do, right? If we have not, go back and repeat a certain set of instructions. If we have, then drop out of this loop and store the data back into memory. So as you can see, there are some kind of, well, it's not clear what exactly initialization instructions are. Are they arithmetic instructions? Are they memory instructions? We'll see a couple of different ways by which this can be implemented. This of course is a memory instruction, right? Load data from memory into a register. This of course is arithmetic, so is this, and this one here is clearly a branching or control flow type of instruction. So writing it out in English or in some kind of pseudocode like this is easy enough. Humans can understand it, but we need to provide it in a form that can be interpreted by a computer. So we would like to convert all of these instructions or all of these human readable steps into some kinds of pattern of zeros and ones, right, bits, that can then be stored somewhere in the memory of a computer, and the computer can then go about processing those instructions. So, a couple of things to keep in mind: not all instructions are available on all CPUs, right? And an example of that would be that many CPUs, at least simpler microcontrollers and so on, do not implement a multiply instruction. So, if you wanted to multiply two numbers together, there is no instruction to do so. That does not mean you cannot multiply. What it means is that you need to replicate that behavior through other means. Okay. Now, an even simpler example is, how do I initialize a register to a given value, in this case to a value 0, okay? And there are many different ways by which this is solved in different processors. There are some computers or some processors, right? Actually, what the technical term for what we are looking for over here is, what we are defining over here is effectively what's called the instruction set. And when I say a processor or a computer, what I mean is usually a family of different chips that share a common instruction set, and that instruction set is called the instruction set architecture that I am building on, the ISA. Right? Most of you would probably be having laptops or desktops that have Intel x86 based ISAs. Some of you may have Apple, right, in which case, depending on if it's the M1 chip, then that uses a different ISA called the ARM ISA. Most of you probably have mobile phones, smartphones, right, which almost without a doubt are running ARM based ISA processors, right. So, that is sort of one of the defining characteristics of the processor. There are many different chips that belong to a common family, and what we are describing over here are different properties of those families. So, when I say, for example, that not all instructions are available on all CPUs, typically I am grouping them by family. Something that is available on an x86 processor may be available on an ARM processor, but probably with a different name. Even within ARM processors, there might be different variants, some of which maybe have a multiply instruction and some do not. Okay. So, if we look at the problem of how do I initialize a register to the value 0, there are many different ways of doing it. One of some types of processors just have an instruction called move, right, and effectively what it says is move the value 0, right, into the register R1 explicitly, right. It is just sort of load the value in here, right. Now, where did the 0 come from? This is usually what is called an immediate operand, right. In other words, it is part of the instruction itself. It is not being picked up from somewhere else in memory or some other part of the processor. It is given as part of the instruction itself. Same way, I could also have something else. In case I have an instruction that takes two immediate values, right, I could say add 0 and 0 and put the result into R1. Okay. This kind of instruction is not very common. You typically do not have instructions that add two immediate values, for one very simple reason. If I knew both of these values ahead of time, I should probably have just done the work at the compilation phase and not, given it as a step for the computer to do, right. So, this is not a common approach, but it could be done. Yet another approach is, for any register, assuming that I have some kind of an arithmetic unit, if I take the register R1, subtract it from itself and put the result back there, then R1 is now going to be equal to 0. It does not matter what the original value of R1 was, right, assuming that your arithmetic unit has been implemented properly. So, this is yet another way of implementing exactly the same thing. R1 will finally have the value 0. A similar thing works with the XOR function, right, where when I XOR two multi-bit values together, what I mean is I am taking the XOR function, right, bit by bit. Now, the XOR function is hopefully familiar to you. If not, then it is one of the digital logic gates. You do not really need to know too much about it at this point. So, if you are not familiar with it, then we can just ignore it, but it is something that you would encounter as one of the more common types of digital logic gates. And finally, there is a similar kind of approach which is used, for example, in processors like the RISC-V architecture, right, where it is assumed that one of the registers in your system, typically R0, is assumed to be 0, right? It is hardwired to 0, meaning that I cannot change the value of R0, it is always going to be 0. So if I know that R0 is always going to be 0 and I try adding an immediate value 0 to it, my result is also going to be 0, which I can then put into R1. Okay. You might wonder why so many complicated ways of doing the same simple task, and the bottom line is, this is simple enough that yeah, you could make a decision that you don't necessarily want to implement different ways of doing it. On the other hand, each of these instructions might be useful in its own way. For example, you want to have a subtract instruction, you want to have an XOR instruction, you want to have an add immediate instruction for other purposes, and all that we are saying is the same thing could also be used for initializing a value to 0. So with that in mind, the instructions that we wrote earlier for adding n numbers could possibly get translated something like this, right? So R7 equal to 0. You will notice over here that now I changed the counter from R of 0 to R of 7, right? The point is it could be anything, any register within the processor can be used over here, and the example that I am going to be sort of working out over here is based on the RISC-V architecture, right? As I said, it is one of the many different instruction set architectures that are available, right? But the sort of one of the properties of the RISC-V architecture is that R of 0 is hardwired to 0, so I cannot change it. So an instruction such as R of 0 equal to R of 0 plus 1 would be meaningless in RISC-V. So I changed it, I made it R of 7, okay? Nothing else has changed as far as the program is concerned. So now if I look at that and say, okay, how do I set this R of 7 equal to 0? The first thing I am going to do is take this, which is human understandable, and convert it into some kind of a standardized format that is sort of easy to translate into a set of numbers, okay? And what I mean by that is, the moment if you look at this instruction carefully, you will see that it has a regular structure. There is an instruction, there are two source registers, or a source register and an immediate value out here, and a destination register, okay, or at least that is the convention that we follow. If most of my instructions have a similar kind of structure, I can readily come up with a mapping from these instructions into some kind of numbers that say, okay, this number is this code, so maybe code number 7 corresponds to add I, code number 23 corresponds to subtract, right? How do I come up with those numbers? You could just make them up. Fortunately for you, somebody in the RISC-V standardization committee has already done that job for you, and rather than just making up numbers, they have used years of experience in actually designing processors to come up with a sensible mapping of values, which makes it easier to build hardware for such things. Bottom line is R of 7 equal to 0, one way of doing it would be this add I R7 R0 0, okay. Like I said, there could be other ways as well. R1 equal to 0 would also pretty much look the same, right? So now what do I do with this? This is good, it is a first step because I have taken something which was clearly meant for humans and started converting it into something which has a very regular kind of pattern to it, and I want to convert it into numbers. How would I go about doing it? This picture that you see before you is an extract from the instruction, from the reference manual of the RISC-V processor, right? And what it shows is, on the right hand side you have all of these names. Like I said, it is just a portion, it is a snippet, right? There are many more instructions, I have omitted most of them, just shown you some that are relevant out here. So what is here on the right hand side is the name, or what is called the mnemonic, right? The mnemonic is just a sort of a way of remembering what a particular instruction stands for, okay? And in this case, I have, for example, add I as one of the instructions that is useful for me. Now, what this table is showing us is that the add I instruction corresponds to a set of bits which is given by this long pattern out here, right? And what exactly does that mean? If you look at it, you will notice that this entire width out here is 32 bits. Okay, that is because I have chosen the 32-bit variant of the RISC-V architecture. There is also another variant which is 64 bits wide and so on. Now, out of these 32 bits, what the encoding tells us is the first 12 bits out here are going to be used in order to store the immediate value to be added. In other words, this 0 that I have out here. Okay. So what do? I can take those 12 bits and write them out in this way. A 12-bit representation of the number 0 is this 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, right. Remember, this is typical binary where having leading zeros does not change the value of the number that you are trying to represent. Okay, so far so good. What else is unknown in this add I instruction? RS1. Okay, RS1 basically says which is the source register for my operation, and in this case R0 is the source register, right. I am trying to add something to the register 0. So RS1 gets the value 0, 0, 0, 0, 0. Why 5 bits? Once again, a property of the RISC-V architecture, right, where they have defined the architecture as having 32 registers. Therefore, a 5-bit address can be used in order to indicate which of the 32 registers you are referring to. In this case, I am going to use all zeros to represent R0. Okay. And finally, I want to take the result and put it into R7, which in this case has to be specified as RD, the destination, and 7 in binary is 0, 0, 1, 1, 1. Now, apart from all of this that we have over here, you will notice that there is one chunk of zeros in the middle, and this pattern 0, 0, 1, 0, 0, 1, 1 out here on the right hand side. They are both important, right? These are very much part of what makes the instruction an add immediate instruction, right? So if I then take all of this, right, and write it out one after the other, I get a 32-bit value out here, which I can then convert into hexadecimal because it's easier for me to sort of read and handle hexadecimal and say, okay, these first 4 zeros get mapped to hexadecimal 0. The next 4 get mapped to hexadecimal 0 again the same holds for the next 2 and also for this one, right. After that, I find when I get to the RD part, yes, this 0011 gets mapped to hexadecimal digit 3, this 1001 gets mapped to hexadecimal digit 9, and the final 0011 becomes hex digit 3. Okay. So you will notice that out of RD, the way that it was written, out of the 5 bits that were there, 4 of them formed one hex digit and one of them got grouped with some other bits and became another hex digit. It does not matter, remember that this entire hex code is only for us to sort of remember this more easily, right. The computer just sees the sequence of bits. Now, hopefully this gives you a fairly reasonable idea about how an instruction that I started with has got mapped into a number, which is basically a set of bits, and these bits, by storing them somewhere in the memory, I should be able to pull them out as required, right, based on the program counter value, and start executing instructions or run a program, so to say. So therefore, to summarize what happened, in the RISC-V 32-bit instruction set architecture, the specific instruction add I R7 R0 0 is exactly represented as this hex code. Okay, so this number in hexadecimal converted into bits and stored in the memory would essentially get interpreted by the processor as an instruction add I R7 R0 0, or in other words, set the register R7 to the value 0. Yeah. Now clearly other encodings are possible, right, because what I have got over here is a full 32-bit value and I have used it in order to encode one of these instructions. Okay. If you think carefully about it, you will realize that out of those 32 bits, some of them are being used in order to store RS1, some are being used to store R2, and 12 of them are being used to store the immediate value, right. So these 5 plus these 5 plus these 12, 22 bits are actually required in order to give me data that makes this particular instruction unique. But the remaining 10 bits were just arbitrarily chosen like this. Were they really necessary? Did I have to set only these values for add immediate? Other encodings are possible for sure. Okay, and in fact shorter encodings may also be possible. right? Meaning that maybe I don't really need a full 32-bit number in order to represent this particular instruction. For example, 24 bits might have been enough, right? Or maybe it's possible to even encode into something even smaller than that, right? But that's not the point I'm trying to make over here. The point is encodings are possible at all in the first place, right? In other words, I can take instructions and convert them into numbers, and that is the key observation here that you should keep in mind. Why is it important? Because at the end of the day, this tells you how exactly even the programs are stored inside the memory of a computer, right? And that in turn has an impact on how memory is used for the different purposes of storing programs, data, switching between the two, the fact that some programs can themselves be treated as data, some data can in turn be interpreted as instructions, and so on. A lot of different interesting sort of variations come up on this the moment we realize that such encodings of instructions into numbers is possible. Let's just take one more instruction as an example, right? This is corresponding to what I had in my code as R2 is a memory load instruction, right? It basically accesses memory corresponding to R of 7, right? It loads data from there and puts the result into R2, right? This would get translated into the mnemonic LW for load word, right? And what I am saying is, what I want to load over here is, I want to load something into R2, so R2 is my destination. The source register is R7 and an offset of 0, right? Because rather than just saying mem of R7 being loaded, this actually allows us to do something slightly cleverer than that. What it says is, I can take the value R7, I can add an offset which I give as an immediate value out here, right? Take that result R7 plus 0 in this case, use that to look up a value in memory, and whatever data I get back from there, put it into R2. Okay, so R2 will get the value which is in mem of R7 plus 0. That is what the LW instruction does. How would I encode that? The first thing is, I have my immediate value which is 0 in this case, right? So 12 bits of zeros. RS1, RS in this case is 7, so I put down 00111. Then this 010 which is part of the instruction just gets copied down here. RD is my destination register, right? So that becomes 00010, right? So this is the binary representation of the value 2. And finally 5 zeros and 2 ones, okay. Once again group it into 4s, I get 0, 0, 0, 3, A, right, because 1010 is the decimal value 10, which is the hexadecimal digit A. 0001, 1, 0, and finally 3, okay. So 0003 A103 is the hexadecimal representation of the instruction load word R2 from mem of R7 plus 0, okay. So these two examples were basically to show you how with one possible example instruction set like RISC-V, I could take my steps which I had initially written out in a sort of human understandable format, convert them into mnemonics and assembly language which is specific to that particular processor, and finally convert it into a number which will go sit somewhere in the memory of that computer, right, which means that we need to think about memory organization, right. And what we are saying is, if I take the example that let's say I have a 32-bit wide memory, what I mean is that each value stored over here is 32 bits, right, and obviously there are addresses that decide which of these values I am reading out at any given point in time, right. If I have a 32-bit wide memory and if I say that overall in this memory there are 1 million locations, what that means is each value here was 32 bits, which is 4 bytes, where a byte is defined as 8 bits, right. So a 1 meg locations would correspond to 4 megabytes, of memory, right? You are probably working on a system that has a few gigabytes of memory, right? By the way, the word that is usually used for the memory that is used over here is RAM, random access memory. And the reason for that is I can basically just go in there and any address that I want to, I can pick out the data that is over there and read it, okay. So random access memory, in this case I am assuming I have a total of around 4 megabytes. In that I am arbitrarily deciding that the first 200k locations are going to be used in order to store code. What do I mean by code? It's the encoding of the instructions corresponding to whatever programs I have written, right. 200k locations basically corresponds to a program size of around 800 kilobytes, and I have also arbitrarily decided that the next 300k locations correspond to data. What kind of data? Depends on what the program is, right? Maybe there are some arrays of numbers over there, there might be a whole bunch of pixel values corresponding to an image, right? There might be the text corresponding to a text document that you are trying to edit. All of that put together, what I am saying is I have 300k locations, which basically is 1200 kilobytes or about 1.2 megabytes of memory, okay. The important thing to note over here is this big box is just memory, right. By itself it has not made a distinction, there is no physical distinction between code and data, right. Which part of it is code and which part of it is data, that's a convention we have chosen over here. I just put it down, and if you follow this convention, then yes, 200 kilobytes of or 200k locations correspond to code and 300k locations correspond to data. You could change this around. If you had a smaller program but wanted to process more data, you could have a different kind of memory organization. This gives a lot of flexibility and control to the programmer or the user of the computer in terms of how exactly they are going to manage the memory that is available to them.